In this video, we introduce two new types of equations which you need to become proficient at solving, exponential and logarithmic. Let's get started. So recall, we had properties in our last video of logarithms, and some of these properties are going to be essential in helping us solve logarithmic equations. So the first property involves recognizing that on one side of the equation, you have a logarithm with a base, and on the other side of the equation, you have another logarithm with the same base. If that is the case, and if the coefficients of each logarithm, the number in front, are both 1, you can simply recognize that the only way for that to be true is if their arguments, in this case m and n, are equal. So one thing that you'll notice is if I have a logarithmic equation where I have a log with the same base on both sides, coefficients of 1, I can simply set their arguments equal. And we'll see examples of this later on in this video. If, for example, I had log base 10, so I just write log, of x plus 2 equals log, again, implied to be base 10 if it's not written, and let's say this is 5, the number 5. Well, I could know right away that the only way for this to be truly equal, that this logarithm on the left equals this logarithm on the right, is if the arguments were identical because they had the same base and their coefficients were 1. So if x plus 2 has to equal 5, which is what I would normally recommend you write down, especially as it gets more complicated, you can see that the answer for x to this linear equation would be x equals 5 minus 2 or x equals 3. And before you say, I'm right, I have my answer, it's really important to check if your actual answer is possible in real life. What I mean by that is the argument of a logarithm always has to be greater than 0, because if not, it's not going to satisfy the eligible criteria for domain. You can go back to our videos on logarithmic graphs, and you can remember that the graph of a logarithmic function, assuming it hasn't been shifted yet, starts off here where x values are greater than 0. This graph has been shifted to the left 2 units, meaning your asymptote is now -2, and you look something like this. So we're really saying, will that graph ever hit log of 5? Well, you notice that as long as your values are bigger than -2, those are legal inputs. So in this case, 3 is bigger than -2, that's a valid answer. But if I had an answer of -3, and you put -3 in for x into one of the arguments, you would end up getting a negative result, and that would be disqualified. You can't have any inputs that are not in the domain. So that's one thing to check at the end. Are your arguments greater than 0 at that input? Okay, so with that in mind, let's head over to our second type of situation. The second type of situation we'll see is if we have a logarithm equaling a number. Now, there might be some condensing that we'll have to do for both of these scenarios, but once you've condensed completely, the question you have to ask yourself is, do I have a log equals a log with the same base, coefficients of 1, in which case I set my arguments equal, or do I just have a log equals a number? If I have a log equals a number, I'm going to recommend strongly that you switch back to an exponential equation to solve. So in this case, you see log base b of x equals some number r. We can switch back to exponential by taking our base to the number on the other side as our power and equal that to our argument. In this case, b to the r would equal x. For example, suppose I had the natural log, and we had, let's see here, how about x here equaling 5? This is saying the natural log of x equals 5. Well, what's the implied base? That's right, it is e. So in order to find x in this case, I would take e to the 5th power and make it equal x. So I would say x equals e to the 5th power. I could then input that into my calculator to see what kind of number I'm getting. It should be a positive number because e is approximately 2.71. And if you multiply that repeatedly 5 times by itself, you should get another positive, bigger number, which is perfectly legal for your input, for your argument. As long as your arguments are greater than 0, they're valid inputs. Okay, so now we've talked about the two ways to solve logarithmic equations. Let's see if you can identify, in the example below here, which of these methods you would be using. Okay, so you have log base 10 of x plus log base 10 of x plus 9 equals 1. In order to get started, what do you think is my first step? If you said condensing, you were correct. Always condense so that you can get a single logarithm on each side of the equation whenever possible. Again, when is that possible? Same base and leading coefficients of 1. Base both of these are 10, so how did we condense a sum of 2 logs with the same base whose coefficients were 1? That's right, we did multiplication inside the argument. So the first argument was x, the second argument was x plus 9, and we would have logarithm base 10, so maintain your same base, of that new product argument equaling 1. Now, if our base is 10, we can continue with this problem. But I will tell you, many students give up right here. They'll say, oh, I condensed, I'm done. No, you just done step 1. The next thing you'd have to do is solve the actual equation. When someone asks you to solve an equation, they're asking you what possible answers for x would make this true. Are there any answers for x? And so you need to continue until you find those x values, those potential answers. So to do that, I recognize I'm in situation number 2, aren't I? Where I have a logarithm equals a number. The base is implied to be 10. So what is the game plan? That's right, switch back to exponential. This time 10 to the 1 is just 10, but if this number 1 was actually a 2, we would have to do 10 to the second power, which isn't 20, but 100, okay? So be sure you understand how to work with exponents carefully. So 10 to the 1 is 10, and that equals my argument, which I could distribute right now and get x squared plus 9x. Now some students make another error here. They say x times x plus 9 equals 10, which is true, but then they set each a factor of that product, like x and x plus 9, equal to 10. That's not possible. I think what they were thinking is that if I have a product that equals 0, I can set each factor equal to 0. But that's not the same thing as setting each factor equal to some other number. So what I have to do to solve a quadratic equation from our previous math videos is get 0 on one side. So this would become x squared plus 9x minus 10 if you subtract 10 on both sides. And then either factor, or in most cases, you'll have to use the quadratic formula or complete the square. This one does factor nicely. What factors do I have? Yeah, x plus 10 and x minus 1. Factors of negative 10, different signs, which add up to 9x. So we end up solving by letting each factor equal 0. That's the 0 product rule. So either x equals negative 10 or x equals positive 1. Now, before you declare your victory over this problem, you have to check if those answers are even possible. What we're saying is, when could this side of the equation on the left equal 1? And the answers are maybe when x is negative 10 or 1. Well, at negative 10, look what would happen in the first argument. You'd have log of negative 10. Can I have a negative argument? No. So negative 10 is not a valid input. It is not a possible x value in the domain. 1, on the other hand, if you put 1 into this first argument, that's still 1, and that's bigger than 0, which is okay. Similarly, 1 in the second argument would give you 1 plus 9, or 10, in that argument, which is still bigger than 0. So that satisfies the domain of this function. So I would say that my solution would only be 1, and if you wrote a solution set, you would just stick the 1 inside. That would be the only solution for that equation. Sometimes it's not possible, but in this case, that's where the graph would hit 1. When x equals, that's when the graph, that is when the graph would hit 1, when x is also 1. So you would have a point at 1, 1. When x is 1, y is 1 for the equation on the left. Okay, so take a look at those methods, make sure you have them in your notes clearly, and then we'll proceed to example 2. Okay, so in this example, it says, could you solve this logarithmic equation? Negative 2 log base 4 of x equals log base 4 of 9. Is it, in its current form, in a position where you recognize what to do? Not quite, right? We had a log equals a log, which is almost what we have here, same base, right? But what is not quite right? If you said negative 2, you are correct. We can't have a coefficient that's not 1 here if we're going to set the arguments equal. We have to have log base 4 equals log base 4 and then set the arguments equal. So what could I do based on our properties last time, in our last video? What could I do with that coefficient to remove it somehow? If you're thinking divide, that really wouldn't help because you'd end up with negative 1 over 2 on the other side, so that wouldn't help much. But there was something called the power rule that said I can bring up any coefficient of my logarithm as a power of the argument. So this would now become log base 4 of x to the negative 2 equals log base 4 of 9. Now do you recognize which scenario we have? Yeah, a log equals a log with the same base, coefficients are both 1. That means I can set my arguments equal. That's the only way this makes sense. If these two sides of the equation are truly equal, because you have the same base and a coefficient of 1, the arguments are the same. So that would mean I'd have x to the negative 2 must equal 9. Okay, but what does a negative exponent really mean? That's right, they're reciprocal. So this is saying 1 over x squared gives me 9. Now, if you don't know how to solve this type of equation, it's called a rational equation. You can look up videos on the internet if you need help solving these. But if you have a fraction equals a fraction, one way to solve this is to simply cross multiply. The other way of thinking of it is clearing fractions by multiplying both sides by the least common denominator. The denominator of 9 is a 1. So right now you could just multiply both sides by x squared and it would get rid of all denominators. Or if you think of just cross multiplying, x squared times 9 gives you 9x squared, and 1 times 1 gives you 1. So you end up with x squared equals 1 over 9. But what is x? Well, this is what we call the square root method, right? X equals positive or negative square root of 1/9. But I can go further because the square root of 1/9 is really the square root of 1 divided by the square root of 9. And we know both of those are perfect squares. So we end up with what result? That's right. The square root of 1 is 1. The square root of 9 is 3. So you should have 1 over 3. So we're having two possible answers. Either x is negative 1/3 or x is positive 1/3. Both of those satisfy that quadratic equation. But do they satisfy the input requirements of the original arguments? The original argument was x on the left side of the equation. So could x be a negative 1/3? No, x has to be, in this case the argument, x, has to be greater than 0. So the negative would not work. But could x be positive 1/3? You betcha, that's bigger than 0. So my solution set would only have positive 1/3 as the answer there. Go ahead and try the second one, part B, on your own. See which type it is and if you can execute it correctly. Okay, so what was your first step? Did you condense? I hope so. Same base logarithm being added. How did we condense those two logarithms? If you said multiply the arguments, you were correct. So it's still log base 10 of x times x minus 21 equaling 2. This is just like the one on the last slide. If you haven't already done so, finish the problem yourself. Okay, so to finish the problem, did you take base 10 to this power 2 and set that equal to your argument? In other words, if you have a logarithm equals a number, you switch back to exponential. This was the second type of situation on the last slide. So this time it's not 10 to the first power like last example, it's 10 to the second power. Or if you want to write 100, you'd be correct. Equaling x squared minus 21x. Okay, so how do we solve a quadratic equation again? If you said we need to get 0 on one side, you are correct. So 0 equals x squared minus 21x, and it was 100 positive on the left side, right? So if I move it to the right side, it becomes negative 100. Most students make their mistakes with sign errors, so be sure to watch yourself very carefully. So now I would have something that maybe could be factored. We would ask ourselves, what factors of negative 100 with different signs would give me negative 21x when I add them up? Well, 25 times 4 is 100. We could use different signs and make one of them x minus 25 and the other factor x plus 4. If you can't read that, that's x minus 25 and x plus 4. Okay, so if I set each factor equal to 0, x could be 25. Or if you set x plus 4 equal to 0, x could be negative 4. Do both of those answers satisfy domain requirements for our input? Well, 25, if you input 25 into your first argument, that's greater than 0, so that's okay. And 25 input into your second argument, 25 would be x, minus 21 gives you 4. That's still greater than 0. So it looks like all of the arguments are satisfying the requirement of the domain when x is 25. But what about when x is negative 4? Does being negative alone tell you that it's not valid? Not quite. What if I had, for example, an argument that was x plus 5? Well, putting a negative 4 in for x would still keep the argument greater than 0. So don't just assume that if you see a negative value for x in your answer that you can just throw it away. You have to check each argument and see if it keeps the requirements, right? If it satisfies the requirements. Negative 4 fails on both counts because it's not only going to fail here because x is clearly negative, not greater than 0, it even fails here. Negative 4 minus 21 would be negative 25. That is clearly not within our domain restrictions. So the only answer that's actually allowed would be when x is 25. Again, if you're struggling with the idea of understanding why are there some solutions that don't work, when you solve a quadratic equation, you get two possible answers. But those solutions, while they are definitely answers to that quadratic equation, they may not satisfy the original restrictions that you had to work with. And that happens all the time in life. You're trying to satisfy a real life situation and you find out that the solution that is possible isn't actually practical. So you actually abandon that path and do something different. Same thing here. While negative 4 would satisfy the quadratic equation, it wasn't feasible, so we throw it out. Okay, let's go over to our second type of equation that we need to talk about today. Not logarithmic, but the inverse, called exponential. So exponential equations also will occur in one of two scenarios for you. The first scenario is the easier case, and that will be if I notice that on one side of the equal sign I have base b, let's say, and on the other side of the equal sign I also have base b. Now what you need to notice here is that we have the exponential parts isolated, right? We don't have some coefficients in front of them. We don't have multiple pieces. We just have a base equals a base, and they're the same. If that's the case, it must be that the exponent must equal each other. The exponents must equal each other. So take a look at what we get here in case number 1. We get something like x equaling r. The exponents are equal. Could you apply that technique to solve 2 to the x equals 8? That is an exponential equation. Notice it's very different than x squared equals 8. Some students get those confused. One is exponential on the left, and on the right, that's quadratic. Quadratic, we have different methods to solve, right? We can use the quadratic formula, the square root property, factoring, completing the square, etc. But exponential is when x, or the variable that we're solving for, is in the exponent. So in order to solve this, we would need to recognize if it's in the first pattern here. In other words, can I recognize that I have the same base on both sides? Well, yeah, isn't 8 really 2 to some power? 2 times 2 times 2, in fact, or 2 to the third power? So some people can do this problem in their head because they can recognize 2 to what power gives me 8? The answer is 3. And if you did that in your head and said, Professor, I'm not going to write all this down, you're fine. That's cool. But I will tell you, knowing this procedure, this algorithm, this technique will be very useful to you when it gets more complicated. If you can recognize I have the same base on both sides, my first step will be to set the exponents equal and then solve from there. This time it's easy, sometimes it's complicated. So x have to equal 3 to set those exponents equal. Now, more complicated situations arise. You can see the example below when you have to first isolate the exponential part. Okay, so if I were to isolate the exponential part here, what would I do first? This is something students really struggle with. Do I undo the multiplication first of 2? Do I undo the subtraction of 7? What do I do first? Well, if you said, I want to divide by 2, while that's not completely illegal, what would you be dividing by 2? If you say, well, I want to divide this term by 2 and this term by 2, and I get 5 on the right, and I just get the 3 to the 4x minus 5 on the left minus 7, you would be incorrect, because what you would have failed to do is divide 7 by 2 as well. All terms would have had to be divided by 2. So wouldn't it be easier if instead of having that nasty fraction to worry about, if we first moved 7 to the other side? And that's my recommendation. If you have a lot of pieces in an expression and you're trying to isolate the exponential piece, take care of the addition or subtraction first. Then undo any multiplication or division. So that's what I would recommend here. Add 7 to the right side and the left side. You'll get 17 on the right. And now you just have the multiplication of 2 times 3 to the 4x minus 5. Okay. Now there's another mistake I see students make. We talked about how our next step is going to be dividing by 2, right? But many people are tempted right here. You don't have to raise your hand, I wouldn't see you anyway. But many people are tempted to first multiply 2 times 3 and make this base 6. Why would that be illegal? Any thoughts? Well, if you thought the order of operations, you are correct, or PEMDAS, or BIDMOS, depending where you learned your order of operations. The order of operations says we've agreed upon this, you have to do your exponent before you multiply. So we have to take 3 to this power before we multiply the result by 2. If you did 2 times 3, that's very different. That's taking a base 6 to the power, which is incredibly different results. So make sure you understand you cannot multiply before the exponent. So instead, you're going to need to get rid of that multiplication by dividing both sides by that number, by its coefficient. You might want to watch this part over and over again because many students get their problems wrong because they fail to understand what the order of operations is here. This becomes 3 to the 4x minus 5 equaling 17 divided by 2. And you're welcome to use the fraction, or if you like to, you know that 2 goes into 17 how many times? Well, 2 times 8 is 16, right? So this is 8.5. So if you like the decimal instead, that's fine. But now look at what we have here. We have an exponential part, 3 to the 4x minus 5 equals a number. Okay, well that's kind of like part 2 here. What do we do if we have an exponential term equaling a number? So we did all of that work just to isolate the exponential piece. Well, we need to either switch back to logarithmic form, which you could do if you remember how we set those up, or an easier way is to remember that we're allowed to take logarithms of both sides of an equation as long as we use the same base. The ones that I would recommend are natural log, which is base e, or the common log, base 10, because your technology has those buttons on a scientific or a graphing calculator. They're easily accessible, but also because in real-life applications, base 10 is the system we use for our numbers in the United States and in most places around the world. We use base 10, right, for our calculations. So because of that, base 10 is going to be very, very common, and the common logarithm log will be helpful. But also in our financial applications and in our half-life applications and populations that grow exponentially, like in our next video, you're going to notice that E, Euler's number, 2.71 approximately, will come up again and again as a very popular base. So that's why natural log is a very, very common logarithm to use, called the natural log, ln. So if you were to take the natural log of both sides, I highly recommend it. What I would end up with here, in this example, I'll come over my head here in the video here, I would have the natural log of the left side equaling the natural log of the right side. Okay, let me get rid of that number so we get some space here. So what would that mean for this particular problem? So coming up here, we would now have the natural log of 3 to my power 4x minus 5 and of 8.5 on the right, or 17 over 2 if you prefer the fraction. What's the point of doing that? Why do I want to introduce natural logarithms or common logarithms or any logarithm into an equation that has exponents? Well, because we remember, hopefully from our last video, that the only way to bring an exponent from the top back down to the bottom of the line is using logarithms. Now that I have a logarithm in front, I am allowed to bring my exponent down in front as the coefficient. So I now would have something to the effect of 4x minus 5 times, in parentheses, ln 3. And on the other side, I just have ln of 8.5. So what does that mean? Well, that means I have now brought my exponent down, which is huge. This looks really gross to most humans at first, but keep in mind the natural log of 3 is just a number. The natural log of 8.5 is just a number. Your calculators could approximate those for you. So really what we have here is not a nice linear equation. We have 4x minus 5 times a number equals another number. We should remember how to solve these. Typically what students would do is they would approach this with using distribution. So if you were to distribute here, and I'm going to come on over, let's see, back down here. If I were to distribute, I would have 4x times the natural log of 3 minus 5, and let me erase part of this because it's getting a little crowded for my liking. I'm going to erase this part for now. Okay, so you can go back and watch that part if you need to get that part written down. Okay, so let's remove that for a moment. There we go. Okay, so here's where we're at this step. Minus, after the distribution, we have minus 5 ln 3. Okay, where are we now? Equaling ln of 8.5. So what's our goal? Our goal is to get x by itself, but it's already here on the left side. We usually like x on the left. That's kind of what we're familiar with, right? So how would I move a number to the other side? This number here, for example. Well, the opposite of subtraction is addition. So I would add it to both sides. Add 5 ln 3 on the left and on the right, and you should get, on the right side now, the natural logarithm of 8.5 plus 5 copies of the natural logarithm of 3, equaling 4 copies of x times the natural log of 3. Still kind of gross, but you are literally one step away from having the result if you enter it carefully in your calculator. And the step would be, how do I get x by itself if it's touching multiple numbers by multiplication, right? How do you undo multiplication, in other words? With division. So you could do it in 1 or 2 steps. I like to do it in 1 step, but some students do it in 2 steps. I notice that I'm multiplying by 4 and by ln 3. So in one giant step, I could divide by everything touching x. So 4 ln 3. But not just one term, both terms. So I would use parentheses to tell my calculator to add first and then divide by parentheses 4 ln of 3. The parentheses are essential to tell your calculator the right order of doing things, right? Add first, then divide by that total. When I do that, 4 cancels, ln 3 cancels, and I have x by itself. And when you carefully type this into your calculator with all the parentheses that I just mentioned, your answer for x should, let's see if I'm looking at the right one here before I give you the wrong answer. Your answer for x should end up being approximately, for x here, 1.737 if you round it to the nearest thousandth or the nearest 3 decimal places. This should be your final answer. Now, it looks really gross. Could you write it differently? You bet. All you would need to do is condense in the numerator. You could do that simply by multiplying your arguments together after you brought your power up. So that make that 3 to the 5th and then multiply that number by 8.5. You could have a single logarithm there. You could also bring your power up here, make this 3 to the 4th, so natural log of that number as your denominator. So there's lots of ways you can make this look prettier, but all you need to be able to do is get an exact answer with the parentheses in the right spot, enter it into your calculator, and find an approximation. You could then check if this is truly the answer, right, by plugging it back in to x. Especially with your technology, this isn't too bad. 2 times 3 to the power of 4 times my answer, subtract 5, minus 7, does that equal 10? If you use the approximate version of 1.737, be aware that you'll get something a little bit away from 10, not exactly. But if you use the exact answer key on your calculator, you will get the exact answer of 10, assuming that you entered it correctly. If you have any trouble at all with entering these into your calculator, please shoot me an email or come see me in my office. Definitely want to make sure that you understand how to use your calculator. All right, so we have another example for you to do on your own this time. Last one. Solve this exponential equation. 5 to the negative x equals 25. Go ahead and do it. You got this. Okay, let's see how you did. Same base, same base. So this is going to be 5 to the negative x equals what number? 5 squared. So if I have the same base equals the same base, what did you do? Good, you set the exponents equal. That meant that negative x must equal 2. So what is x? We know what negative x is. The opposite of x is 2. So if I divide by negative 1, or if I think about it, I know that the answer must be positive x equals negative 2. Does that make sense if I check back to my original? If I take 5 to the opposite of negative 2, that's really 5 to the 2, which is 25. So I know with confidence that the answer is negative 2. That's the easiest type of exponential equation you could ever solve. Most of the time you have to isolate first, so make sure you practice like we did in the last slide. Now B is a lot harder, isn't it? Pause the video, see if you can try it yourself. So what you should have noticed right away is that they had different bases. That means I can't use the same trick I used last time. Instead, what do I do to bring down my powers? What should I take on both sides? If you said natural log, you are correct. You could also do the common log, but I recommend getting used to natural log. It's more helpful in many formulas and applications. So when I do that, I would now have the natural log of each of these exponential pieces. 5 to the 1 minus 2x on the left, and 2 to the x plus 1 on the right. By doing that, what do I have the power or ability to do now? That's right, I am able to bring my exponents carefully down on the line as coefficients. So in parentheses now, I would have something like parentheses 1 minus 2x times the natural log of 5, equaling parentheses x plus 1 times the natural log of 2. In the last example, we talked about how to handle this. See if you need to go back and figure it out yourself before you watch me complete this. Okay, what you did hopefully was distribute. Let's see how that went. If you distributed correctly, you would have had 1 times ln 5, which is just ln 5. Good job. Negative 2x times ln 5 is negative 2 copies of x ln 5. All of that business needs to equal the other side after you distribute carefully. X times ln 2, well, that's just x ln 2. Just juxtaposition, multiplication. 1 times ln 2 is just positive ln 2. Okay, if that's confusing, just keep in mind this is a linear equation, right? How do you solve a linear equation? You get x by itself on one side. So every term that has an x you need to put on one side, and every term that does not have an x you need to put on the other side. So you need to pick which side would you like x to live on. If this were me, I'd probably want to keep x positive, just my preference. So I'm probably going to recommend that you move negative 2x ln 5 to the other side by adding it, which also means the terms without x I'm going to put on the left side, so I'm probably going to subtract the natural log of 2 on both sides. Where does that bring us to? Well, let's take a look. I'm going to erase part of the first problem so I have some more space. Okay, so hopefully you have that in your notes so you can watch the video again for that part if you need to copy something. Okay, so looking at what we have here, what would be my next step after I have subtracted or added correctly to both sides? Good, I would have, at this point, the natural log of 5 minus, good, the natural log of 2, so that was this guy moving to the other side, well done, equaling, if I move 2x ln 5 over as a positive by adding it, I would have maybe x ln 2 plus 2 copies of x ln 5. Still kind of gross, but we have the x terms on one side. If you're really paying attention, you could show me that you can condense here. ln 5 minus ln 2, how does that condense? If you have division of two logs with the same base, coefficients of 1. That's right, if you said natural log of 5 over 2 or 2.5, that's the same thing, isn't it? Just makes it easier to write. And similarly, we have an x and an x. What do I do if I want to bring an x in front? That's called factoring out the common factor. Good job. So if you factor out an x, that would be natural log of 2 plus 2 copies of the natural log of 5. Well, you are now only one step away from knowing the right approximate answer in your calculator. You could also clean this up if you wanted to, like you could make this 2 become the exponent of 5 in the argument, which is 5 squared or 25. So if you really wanted to, you could have x times the natural log of 2 plus the natural log of 25 would really be the natural log of 2 times 25, or 50. So if you wanted to write it a little bit cuter, that would be the condensing you could do. You didn't have to do that, but at this point now you'll be able to see the problem and the answer a lot cleaner. So let's see what happens. When I get x by itself, that would mean I need to divide by whatever's touching x. So dividing by whatever is touching x, that's ln of 50 in this case, if you condensed it. And I encourage you to condense if you know what you're doing. If you don't feel comfortable condensing, then just be sure that you use the parentheses correctly and carefully at the earlier step. This point, now x is by itself. I would claim x should equal this exact answer, the natural log of 5 over 2 or 2.5, divided by the natural log of 50. Keep in mind you need both natural logs here. You can't just write one of them. That would mean something different. And the approximate answer that you should get in your calculator for x is about 0.234. And you could then check that in the original problem on the left and on the right. When you plug those answers in exactly or approximately, do you get basically the same thing or exactly the same thing, depending upon which one you entered. Okay, so we've now talked about the two methods of solving equations today, logarithmic and exponential. Pattern recognition is key. Solid algebra skills, being able to isolate a variable by itself correctly is key, and a lot of practice is key. If you have any questions about anything we did in this video, please reach out to me right away, and then remember to practice, because math is not a spectator sport. I'll see you next time.